You're good. Just want to make sure you were okay.
No, this is the happiest I've been in a while.
Gotcha. Some sounds could be either good or bad. Hey. Let's see. Josh. Rain is still out. Tegan, JC. Based on what?
Based on my friend, because he's like a chicken collector.
Oh.
Yeah, so the next verse.
Okay.
Yeah, based on.
I'd be curious to find out what variables he used to. I thought it was like an online quiz thing. What chicken would you be?
Based on personality.
Oh, I see. Okay.
That's what I was thinking.
Gotcha. Everybody should know what chicken they would be. Where's that college course at? Welcome, guys. Welcome to another installment in the ongoing saga of what the hell is going on with statistics. Everybody has this sheet here, right? Does everybody remember what I said about the homework? You don't have it? You need it? You don't want it? Okay. Okay. If not, I appreciate the honesty. I don't have it. I don't want it. You want it?
I need one.
All right. You need it? I mean, you don't need it right now. Just should have it in your possession somewhere. Okay. So guys, last time we finished this. Where do I have one of my finished products? Shoot. There's one thing on here I want to talk about at first. Before I do that, anybody have any questions from homework stuff? I had a few questions earlier, but what did I do with those? Anybody have questions from homework? No, okay. Yes, what you got? $65? All right. So let's see. Previously, an organization reported that teenagers spend 4.5 hours a week on average on the phone. They think that it's higher now, so they choose 15 teenagers at random. Ask them how many hours per week they spend on the phone. Whoa, okay. They don't want you to actually conduct a full test, right? They just want to know what the null and alternative hypotheses are. So let's see. Can you guys find the claim that's being made in this mass of words here? What's the claim somebody's making? Bless you. Is anybody making a claim in there?
Teenagers spend 4.5 hours per week.
No, it's not the claim. It's kind of like what we know from before. So what you look for is words like they feel, they believe, they think, they claim. Sometimes they'll actually say the word claim. They think it's gone up, right? They think it's higher. Okay, so how would you write that claim? What would it look like in Mathish? They think the mean has gone up from what it was before. So how would you write that in Mathish? Say again. Sure. Mu greater than 4.5. I love it. What are the two options for the hypotheses? What are they? So I'll give one of them, the null hypothesis, right? What's the other one? Yeah, alternate hypothesis. Where would this go and why? Yeah, why does it go in the alternate? What goes in the null if it has an equal sign? And this does not. So it would go here. What would go here? Less than?
Greater than, less than or equal to it.
Equal to, yeah. I like less than or greater than. Well. So now all right, before I forget, let me see if they did this. No, good, they didn't do this here. Why can you eliminate A from the beginning? You can see the difference there. Why can I just say there's no way in hell the answer's A? Yeah, I would never make a claim about a sample mean because I could just look at the damn thing, right? The sample's what I got. I'm not going to make a claim. I claim that I have 5 fingers on. Yeah, it's amazing, Jeff. On this hand, by the way. 10 total. So here, part A would make no sense. I would never have a hypothesis about a number I can just look at. The hypothesis should be about the population mean, the thing that I can't get a hold of, right? So A is out. And now we've already written it. So which one matches with what we wrote? Do any of them? Oh, this is one of these. Okay, I knew it. Obviously this guy's out, right? Why is this guy out? Because it references the sample information, right? So it's got to be one of these two. And this book is one of those books. Yeah, they think the mean is higher. Oh, wait a minute. Actually, did they get it right? No, they didn't. Okay. Some books will always have this as an equal to. They'll always have that as an equal to. And that's actually one thing that's kind of funny about statistics is there's parts of it that are not settled. You're not used to this. Most mathematics have been settled for centuries. Are you with me? Especially the math that people at a college will see. That math has normally been settled. Statistics is relatively new, right? Some of the statistics was just being come up with in the early 1900s, which sounds like a really long time ago, but on the grand scale of things, not. Some books will use this. This book kind of alternates between these two. Me, it's always going to be these two have to be opposite. Why? Because that's the only damn thing that makes sense. So I don't know if this is part of the problem. Look at the HA. Which HA matches up? This one. Right? Isn't that what we put for HA? Okay, good. That's not what we have, but that's the answer. So some books and some statisticians will always have an equal sign for the null hypothesis. The reality should be these are opposite of each other. And again, I'm just one person. There are other people out there that disagree with me. Right? So they can walk around being wrong, but that's okay. No, sorry. Is that okay? I don't know if that's the issue with that problem. Because if so, I agree with you. That's a little weird. You're like, you do that and then you're like, none of them match with what I just wrote. But it's got to be option D. Is that all right? All right. I always forget about that. Some books always use equals. Some books never use equals unless it's supposed to be equal. And this book does both. It's a little bit nerve-wracking. Anything else from homework? So that one, I agree, was kind of weird. Anything else from homework stuff? All right. Normally what that means is not enough people have gotten into it yet. Okay. Looking back at this. Just to kind of really quickly review where we left off last time. So there's going to be 5 steps. If you weren't here last time, and even if you were, what did I say about the homework in section 9.5? The book is going to want you to use a worksheet that they reference that's in the back of the book, and you just say, book, you use these 5 steps. They are actually the same, but theirs is out of order because they do theirs entirely in the calculator, right? And you chose an instructor who doesn't do that, so sorry. Okay. So yeah, you have to use these 5 steps. So if I were you, I would have this sucker sit next to me as I do section 9.5 homework. Also, the question we just did was from section 9.1. Section 9.5 is where they have complete hypothesis tests. 9.1, 9.2, 9.3, 9.4, you're not going to have to do the full test. They're going to reference different parts of the test. Okay. So we're definitely going to do more examples of these. But I want to point out one thing that I didn't come back to because there just wasn't time. In step D for the p-value. If somebody could help me remember, because for some reason I did not bring with me the sheet that I actually wrote on. I don't think. In step, maybe it's here. Yeah, good. All right. I don't know which one was us because I did it in both classes. I'll look at this one. So we got down to this step and we got a z-score, a z-star of 3.45, right? So just to really highlight the important parts. Every step is important, but the most important steps are C and D. They are the heart of the test. So if I want to test something, in some kind of test, I can have a benchmark, and I can say, you've got to get past that benchmark to show me evidence. So I gave the example about trying to get somebody on our football team that's fast. So we could have them run some certain amount of length, and they have to show me evidence that they should be on my team, right? So this step sets up where evidence starts, and this step says, did our sample make it far enough away? So let me stop right there. So let me go over this again. The beginning is, what are we talking about? What can I use to talk about it? So in this case, we were allowed to use z-scores. Where does evidence start? Did we make it far enough away to show evidence? And then, what the shit just happened? Your conclusion, right? Okay. So the one thing we did not do on the sheet was the p-value. All right, so let me do this. I'm going to kind of redraw our picture from part C. This is a one-tail test, correct? Can anyone point out to me why this was a one-tail test? What was it about this that made me realize it was a one-tail test? Say again? Yeah? Well, no. The claim could be either one. It could be either one. And the ha is the one that I always look towards. And sure enough, what's the ha tell me? I want to find a sample that is more than. So not only do I know it's a one-tail test, I also know it's a right-tail test. Does that make sense? Less than, it would be one-tail test, left. When would it be a two-tail test? If my claim is something like, we think it's changed, we think it's different, we think it's not the same, whatever, that would be not equal to two tails. All right, let me stop. Okay, y'all look appropriately excited, which is fine. So coming back down here, it's a one-tail test. Can anyone tell me what the area in this tail is? Why are you looking at me? Poor little phone's like, because you pointed me at you. Okay. Can anyone tell me the area in this tail? Okay, I love you guys. Yes, okay. I don't know, do they offer I need to take a lip reading class? Because everybody's always like, if I look around the room, there's people mouthing the answer to me. It's like, if I don't look in your direction, if I can't read your lips, I'm like, damn it, I don't know.
Is everybody cool with that? That's 0.01. That is what told me how to get this z-score, correct? That's how I knew to get 2.326, because alpha is 0.01, one tail. This means that there is a 1% chance of getting a sample in here if the mean really is 10.15. That's what that means. Let me say this again. If the mean really is 10.15, there is only a 1% chance that a sample would show up there. That is what that means. Are you guys with me? So if we get in there, we just did something so unlikely, given that the mean is in the right place, that it's more likely the mean is in the wrong place. It's more likely that the picture is actually shifted over. Does that make sense? So it's exactly like I said, assuming this number is correct. Let's go do something so out of whack with that assumption that that assumption must be wrong. This is called a proof by contradiction. Assuming you're right, look what I just did. Right? So then, therefore, you must be wrong. So let me really focus on this. So we got our rejection region. It's got 0.01 in it. And this was 2.326. What was our Z star from that? What, say it again? 3.45. So Z star, 3.45. So you can put a little star up there. Ooh! Can anyone take a minute? You need your Z-score chart. Can anyone tell me what the area is in the tail of our Z-score, our Z-star? What's the area in the tail of 3.45? Now, where's that, though? Be careful. That would be this way. Is this right? You guys get 9997? Yeah? So, of course, that's this way. So what's in the tail up here? Little tiny 0.0003. Okay. Right? So what this is, alpha tells me what is the biggest, how do I say this? What's the probability that I need to find a sample that's below that will make me reject this? Let me see if I can say this better. 1% chance is the, what did I call it before? The benchmark. I need to get a sample that is less likely than 1% chance. So anything in here has a 1% chance. We got way the shit over there. What's the probability that I get a sample at least this far away? 0.0003. That's stupid small. That kicks the ass of what I said the maximum probability was to show evidence. So, there's a 1% chance that a sample shows up anywhere in here. You guys are all with me on that. Not only did we show up in there, we showed up kind of way out there, right? This number that we just got, that is the p-value. The smaller the p-value, the more evidence it is against the null hypothesis. That is effectively, it isn't perfectly this, but that is effectively the probability that the null hypothesis is true. So there's a 0.03% chance, roughly, that the null hypothesis is true. So what's more likely? The damn thing is false, right? Are you guys semi with me? So the p-value, I want this to make a ton of sense. The alpha is the area in the tail that the critical z-score makes. Area in the tail of our rejection region, right? So the book calls this critical, I'll call it critical. So that would be this. Alpha is the area in the tail that z-score makes. The p-value is the area in the tail that our z-score makes. So what does this mean? If we calculate a p-value and it is less than alpha, that means that our tail is smaller than the rejection region tail, which means we made it further than that z critical, which means we would reject the null. If the p-value is greater than or equal to alpha, we would fail. So again, if the mean really is 10.15, any sample mean should show up in here, right? That's effectively what the null hypothesis says. I think that it's going to be in here. If we find a sample that is out here, that effectively is the probability that this is in the wrong place. We only have a 0.03% chance to get a sample here if the mean is in the right place. And that's why when we make our conclusion, we conclude that the null is wrong. The mean is not this. It's actually more than this. And that's exactly what we said here, right? We said we have found sufficient evidence to support the claim that the live longer. We found evidence that the mean is bigger. Okay, so let me show you some real life examples of p-value stuff. I found a couple studies. Let me see, what do I want to do first? Sure. Almost invariably, studies are not great things to think about. So this is slow wave sleep loss and incident dementia. So no, we're not going to suddenly become a sleep analysis class, so don't freak out. The main thing I want to look at this is some statistics we can now recognize. So for example, look here. What does this mean? What is this? That's a confidence interval. So they're saying, what was this about? Again, I don't want to get too deep into the biology of this, but what is this? Slow wave sleep, I think that's what it was per year, was the risk of dementia. Okay. So this is some kind of a confidence interval for what they're calling a hazard ratio. We're not going to get deep into this. I just want you to realize when you look at any statistical analysis, you will see confidence intervals all over the damn place. If you're going to look at this study, you are more than likely somebody involved in sleep studies, and you would understand all of the words up here. Some of these words, I have no idea what they are. Thankfully, I think I know a lot of them, but not a lot, not all of them. Look up here. That's the p-value. So when they did something about age versus a certain type of sleep loss, that tells me that there's a 0.1% chance that what they saw in the sample they took was just random. It wasn't really one thing affecting the other. So what's more likely is age does affect that type of sleep loss. Do you guys follow? When p-value is small, that is evidence for whatever it is you are studying. That's a lower probability that it's just randomly happened, right? You guys follow? Anytime I took a sample, couldn't I just happen to pick a sample of people that were one way or the other naturally? So there's always a chance that what I see is not reality. What the p-value does is it gives me an idea of how likely is it that what I saw is just from random chance. So there's a less than 0.1% chance that that's what I saw there. So anytime you look at any statistical analysis, you're going to see p-values all over the damn place. They're a quick way to communicate, oh yeah, this thing we just looked at, this is how certain we are that's a real effect, right? There's still a chance that it's not a real effect, that aging has nothing to do with a certain kind of sleep loss. But it's really really small chance. Okay. Let me see. Here's another one that I really liked, but oh wait, is that this one? No, this is a different one. That's right. Okay. This one I like a lot because it's okay. It's kind of like statistics overload, which you guys are like, that's this class every day, Jeff. I know. I like this one a lot, and of course I would, because what are these? What are those? Quartiles. That's right. And this is about coffee, or specifically caffeine intake. And I think this was caffeine intake versus, shoot, what was it? It's your study, Jeff. Be quiet. The risk of physical frailty in late life. Oh boy. So basically what this study found was if you take in a certain amount of caffeine, that actually decreases the chances of certain types of frailty later in life. So real quick, is everybody cool with that? That's the quartiles. We haven't seen those in the wild until just now. So that's kind of nice. There's actually a lot of other shit in here, by the way. I'm going to come back to this study as we learn more things. This last column, see that? P-value. So real quick, this guy, is that a very small p-value? 0.73? No. So that one, now this was a study in, I can't remember, oh shoot, where was it? I can't remember exactly. You could do it, Jeff. Here we go. Chinese adults living in Singapore, blah, blah, blah. Okay. So that's why right here, this was talking about the language they spoke, the dialect group, so the certain dialect of a language they spoke. Cantonese, I know. I'm not sure about this one. It's a new one on me. So does it make sense? Real quick, stay with me. P-value, 0.73. That's not evidence there's a relationship, and that should make sense. There shouldn't be a relationship between the dialect of language you use and the amount of coffee you intake. Would you expect there to be a relationship? If you speak a different dialect, should that affect how much coffee you drink? Probably not, right? There might have been, so they still analyzed it, but that p-value is so stupid big. 0.73 is stupid big. That's like, nope. It's got to be a small p-value to show evidence that there is a real difference there. That it wasn't just some random happenstance. Okay. Maybe. Okay. I think I have one more study, but I'm not going to go through it. This one's kind of funny because anger might help you achieve challenging goals. But I don't know if I want to reinforce that. You told me to be angry, Jeff. No. Okay. So just to make sure everybody's with me on this, the p-value in this case would be 0.003. You can do one more O, 0.0003. Since that is less than alpha, that is another way to find out that I reject the null. I don't know if you feel like this, but when I very first time I taught statistics, it was before I had finished other statistics courses. I didn't know why we did a p-value step. I'm like, I already know the answer. We did the answer before we knew what the p-value was. Here's the reason. In the real world, there is no freaking alpha. In the real world, there is no alpha. So people will report p-values because each person that looks at the study will come to it with their own level of evidence they need. So I might have an internal alpha of 0.01 and somebody else might have a 0.005. I don't know if this makes sense to you. If you guys evaluated some evidence, would everybody come to the same conclusion? Shit, no. So that's the equivalent of everybody's got their own alpha. So in this not real world setting we're currently in, right, in the classroom, they're going to give us alpha because you guys don't have an internal alpha yet. So whatever field you go into, if you specialize in a field, you're going to have kind of an internalized alpha. Anybody going to become a nurse? I can't remember what words. Yes? Okay. Nursing especially, well, there's obviously other ones, but nursing comes to mind because you guys are going to need to be able to read a lot of studies, based on effects of medicine and certain types of nursing procedures and so forth, you're going to need to understand how to interpret what the study says, right? Okay, so you're going to have your own kind of internal feel for what enough evidence should be. All right. So, to find the p-value, you just find the area in the tail that your z-star makes. Okay. So let's do this. Let me give you this. All right, so if you haven't kind of figured this out yet, this will be our life for a few days. We'll be doing several of these. We're going to do a couple examples of hypothesis tests using what we are able to. So one of these is going to be a z-score test. The other one's going to be a t-score test. The hilarious thing is all the steps say the same. The steps don't give a shit, right? We just have to use one chart or the other. Actually, we always use the t-score chart. But, and then I think the last thing I'll do today is talk about what would it look like. What would change if I had to do a hypothesis test for a percentage? Right, so that would be like doing a hypothesis test for the percentage of people that are going to vote for some candidate. You with me? Because all the polls are just polls. They're just samples. So then I can do a test based on that to see if I can kind of verify to a certain degree of certainty who's going to win, right? And then from past experience, we've learned maybe we shouldn't do that. So on the first dude, read through the first dude real quick if you haven't started to yet. Did I remember to change? Yes. Okay. Take a minute and see if you can do part A. So what's the claim in English? What claim is being made? No. So I know where you got that from, but don't forget this. When we're on step A, in the real world, we have not taken a sample yet. We don't know shit. We're just making a claim. Now, hopefully, you know a little bit so we can actually develop a claim. But so at a certain plant, they changed some process at the plant. They changed something. And then we're worried. We're like, okay, how did that affect the assembly time? We don't know. So what is the claim? The very first sentence is not a claim. That is the known fact. The Subaru Forester has a mean assembly time of 27.2 hours, which is known. So we visit a certain Subaru plant where changes have been made to see if their assembly time is still the same as the overall average. So what's the claim? Still the same. So the claim in Mathish is the mean. Still the same. Still the same. Equals 27.2. Okay. So the mean assembly time is 27.2 for all Subarus. There's this one plant that made some change to their assembly line procedure. So now we're curious, is the mean still 27.2? That's going to be our claim. So this is exactly like a court case. And we're going to try to find evidence against that. So we're sort of like the prosecution in this very boring court case about mean assembly time. So I really want to point this out. It's really obvious when it's going to be a one-tail test. You're going to see directional words. What the shit is a directional word? Increased, decreased. We think it's gone up. We think it's less than. We think it's more than. Right? Those are directional words. More than, less than. We think it's gone up. We think it's decreased. The ones that are going to be two-tail tests, you're going to have some trouble figuring out what the claim is, but here it's still the same. Okay, same, equal. So it kind of gave away the game here. It will be a two-tail test. Let's see why. Where does this go? Sorry, every time I ask a question like that, I'm always like, I'll tell you where it goes, Jeff. No, where does that go? Which little dude?
Null.
The null, why?
Because it's equal to.
Because it's got an equal sign. It's the most direct equal sign. So the null always has an equal. So what can the null be? Equal? Greater than or equal to? Less than or equal to. That's all the null could be. Alternate? Greater than, less than, not equal to. So I just gave it away again. What's the alternate going to be? What's the opposite of equal to? Not equal to. Now just to make a little side note, don't write this down. We used to write this like this. Less than, greater than. Kind of happy we don't, but in a way this is nice because this is why it's two-tail. Because how can you be not equal to? You can be greater than or less than. That's why it's a two-tail test. Is that cool? Math people, we don't like more than one sign in a row if it's not necessary. So we said screw that. Okay. So this is a two-tail test. My poor little normal curve. Somebody left that out in the sun. All right, now is everybody cool with that first part? You guys with me? So if you're having trouble figuring out, is it greater than, less than, it's very likely equal to or not equal to, right? Don't say anything. Look and see if you could tell which I have to use. There's two things you have to look for. All right, who's got that? What do you have to look for? What's the first thing we should look for? Is it normal? Yeah. Does it say it's normal? Sorry.
No, I just said standard deviation.
Oh, and then the standard deviation. I love it. So does it say it's normal? No. Shit. But what saves us? Yeah, 73, which is bigger than 30. What'd you learn in school today, honey? 73 is bigger than 30. Wow. And then second thing, like you said, right? So that first thing tells me I can do something. Second thing is Z or T. So what do I look for? Yeah, which standard deviation do we know? Population. So sigma is known. So what am I allowed to use? Z-scores. Kick ass. And just to remind you guys, you're going to have, there's no reason to use these formulas on this. Don't even write this down, but I just want to put this out. On your formula sheet, you will have these formulas. And just to remind you guys, Z is when I have sigma, T is when I only have S, right? So you're going to have that on your formula sheet to kind of remind you, when do I use those? So they don't belong here. Go away. All right, try to set up part C. Oh, go ahead.
Sorry, I missed that for 2 or B 2. I see the standard deviation. What's that second thing?
This word here?
Yeah.
Known. We know it. I'm making it so much better. Sigma. Sigma's known. We know what sigma is. So if I only know S and I don't know sigma, that's when I have to use t-scores, right? So let me see. Let me capture a few things. How many tail tests was it? 2 tail. What's alpha? 0.02. It's right there, Jeff. Amazing. And it's z-scores that I can use. So of course I'm going to look at the t-score chart. And what do you guys get for the z-scores? Good. 2, 3, 2, 6. So there's a negative one, there's a positive one, because there's 2 tails. So when I say define the rejection region, I mean draw this picture. And then I say put it into words also. So what would it take to reject the null? What would our Z star have to do? Either, so I got 2 rejection regions here, right? How do I get into this one? If my Z score is less than, so I'm trying to look around at all my lip people, or Z star is greater than, positive 2, 3, 2, 6. If either one of those things is true, what can I do? What can I do? So let me remind you guys. The null is always the one that has some kind of equal sign. He will always be the one that thinks it's supposed to be in here. Right? He's the guy that says, you should find something in here. If we find something out here, what can we say about the null? It looks like that guy's wrong. So if I get into these, this is why we call it the rejection region. I can reject the null. I can support the ha. All right. So just to kind of back up. First step, what the hell are we talking about? Second step, what can I use to talk about it? Third step, when does evidence start? Fourth step is going to be, did our sample make it far enough away? So go ahead and try to do part D. Don't forget, a sample was taken and we're talking about sample means. So something should happen. All right, let's see. So somebody tell me anything about the sample. Say again? N is 73, I think is what you said. Yes.
The mean is 26.7.
Which mean?
Sample mean.
Sample mean, kick ass. And you're like, you asked for sample stuff, dude. All right, I got you.
27.
Say again?
Never mind.
Gotcha. All right. We also know this is not the sample stuff, but we're going to need this. The population standard deviation was 1.77. And what do I have to do with this? What has to happen with this dude? I've got to change it. Now there's still people. All right. So you got to be really careful. When I do this, it does not become a sample standard deviation. No. It becomes the population standard deviation for all samples of size 73. It is still a population standard deviation. Can anyone tell me the difference between the real difference between these two things? So I'd love if somebody said, well, the other one's smaller, Jeff. Okay, that's right, that's true. But what's the conceptual difference? This is the spread of individuals. This is the spread for groups. Yes? So why can't I use this one? Why do I have to do this? Because we have a freaking group, right? I'm talking about a group. I need to know what all of the groups would look like. So I can't use this number. I can't use the one that works for individuals. I need the one that works for groups. So what this is going to be? 1.77 divided by square root of 73. I love it. I love that. Is that like 0.2 something? I don't know. 207? Okay. Now what's happened sometimes with students is they go, that's a lot of work. I must be done. No. All this shit is just to get ready to calculate this, right? So Z star equals, how do I set up the formula? It's our mean, 26.7, minus the supposed mean, 27.2, divided by, what happened to you, Jeff? Divided by 0.207, that's right. So now throw that in there. It's going to be like 2.46. 2.42? Okay. Negative. Gotcha. Thank you. Negative 2.42, right? Okay. This whole step is old news, right? We've done this kind of thing a lot. But what do I do with this? You guys should be able to tell me the answer right now. Did we find enough evidence or not? Why? You can see it. You could do it algebraically. Negative 242 is less than negative 2326. Or visually, negative 242 would be here. We made it in. So what does that mean we could do? Probably what it tells me here, right? I can reject the hope, and I can also support the hot. I want you to realize something. I'm going to say something kind of weird. I just wrote one thing. If I can reject the one dude, that automatically means I support the other guy. I reject you and I support you. I mean that because they're opposite stances, correct? All right. Any questions at the moment? Please, dear God, speak up now. Yes.
I don't get the reject and support.
Got you. Do you see how the null thinks the mean is this? In fact, no matter what, the null is going to have equals as a part of it, correct? Some kind of equals is going to be there. So the null thinks it should be in here somewhere. The null thinks the mean really is here, so any sample we find should show up close to that. If we find a sample, therefore, that is not close to that, that is evidence the null is wrong. We just did something so unlikely, if the mean really is this, that it's more likely the mean is not that.
Okay, so then if it's wrong, we reject it.
Yeah, if I make it into the rejection region, and this is why it's beautiful we call it the rejection region, I reject the null. If I don't make it in there, I fail to reject the null.
So are we supposed to reject?
We're not supposed to do shit.
Okay, so
I don't
heard
know.
you say fail, so
Yeah, huh?
I heard you say fail. That goes.
Totally, yeah. So that doesn't mean we did anything wrong. It just means there wasn't enough evidence.
Okay.
So in a court case, if the prosecution is trying to show the defendant is guilty and they don't do it, then they did not succeed. They failed, correct? Doesn't necessarily mean that they did anything wrong. Maybe the person really was innocent, right? Give me that back. Okay. So therefore, let me stop for a second again. I really want you guys with me. So, when we calculated where our sample fell, it falls so far away from where we think it should that that's evidence that the middle isn't really here. If the middle was here, then it shows up somewhere more likely. Does that make sense? If the entire picture was moved down a little bit, then the sample would have shown up where it should. So that's why it's evidence that the mean is not 27.2. It's evidence that that middle is not 27.2. It should be a little over. So, did we find evidence? Did we succeed? Yes, we did. So we have found sufficient evidence. 2. So if you fail to reject and so forth, obviously you say, we have not found sufficient evidence. 2. What was the claim again? Which one was the claim? Ho or ha? The null or the alternate? The null was the claim. Therefore, I want to use this language, not this language. Let me say this again. How do I word this damn conclusion that Jeff wants from me? Slap. What was the claim? I used the language that goes with it. So the claim was the null. I'm going to use this language. We have found sufficient evidence to reject the claim that plagiarize. Sort of plagiarize. We have to reference the claim, so we're just going to write down what the claim. What was the claim? The assembly time is still the same, right? So we have found sufficient evidence to reject the claim that the assembly time at this plant is still 27.2 hours. More specifically, it seems to be evidence that it has decreased, right? So if the changes they made were trying to increase the efficiency, it looks like it succeeded. But we went into this not knowing. We went into this like, we made some changes. I don't know what happened. Let's see if it's changed. Does that make sense? Okay. Appropriate levels of excitedness. Okay, so I'm going to talk a lot less now. I would love it if you guys would get together with somebody near you and try to do as much of this one as you can. I will give you one hint. There will be one big difference between this one and the one we just did. What? Yes. Do it in general. All right, guys, let me catch up to you. These are so fun, Jeff. Okay. Guys, help me out. What was the claim in Mathish? Mu is greater than 2806, right? Yeah. Okay. All right. First hurdle. So you can normally find the claim, and you guys are getting more used to looking for the right words. We believe, we feel, we think. The claim, sometimes we even use the word claim, which kicks ass, because you're like, okay, there it is. So you write that down. Does it have an equal sign in it? Nope. So it goes next to the ha. What's the ho then? What's the null hypothesis? Yes. All right, let me stop for a minute. Is that all right? And again, every step of this in the past, there was a choice. And they made this choice. They wanted this guy to be the one that always told me where the rejection region was. So that's the statement that I can actually show evidence for. And since I can never show evidence for equality through a sample, I want this one to always be the one that does not include that option. It can't have an equal sign. Okay, I like it. So how many tail tests will this be? One tail, which direction? Which way? Yeah, up here. So one tail test. All right. So my to show evidence for this, my sample should be bigger. That by itself should make sense. Okay, I like it. All right, what two things do I look for here? First thing is, did I start you up? Yeah. Yeah, sample size is 51, so it's greater than 30. Check. Good old central limit theorem. Be really careful. If the sample size is 22, they might say it's normal somewhere, right? So look for one of those two things. And then what's the second thing I look for? Which standard deviation do we know? Anytime you're like, I don't know which one, that's a sample. I don't know what, this is a sample. It's a sample one. Because if it was a population one, they would actually say freaking population. Because again, that's not a normal thing for statisticians. We don't normally get the full data. We're all excited. We're like, holy shit, I know the whole thing. And another thing, from a sample, we find this and this. Okay, that's a sample standard deviation. S, not sigma, known. You make that word better. Okay. So what does that mean? T-score. This one says I can do something, and this one says specifically I have to use T-scores. So what all do I have to go into this knowing so I can get the right T-score? I have to know what alpha is. What's alpha? 0.01. It's a one-tail test, right? That's basically all I have to know. So if I look up 0.01, one tail, which column am I looking at? Well, I do have to know one more, yeah. Degrees of freedom is what? 50. One tail, 0.01. Don't look here. That's two tails. One tail, 0.01. Stop at 50. Wee-haw. I get that. 2.403 is that? So I saw that number on quite a few people's papers. So let me do this again. I'm going to say this again. If I take a sample, do you all agree with me that the sample mean is bigger? Why is that not good enough to just stop, right? And you're like, it's good enough for me, man. Can I just say it? That's good enough for me. It's my own internal alpha. That's what you know. Why is that not good enough to stop? It's bigger. It's bigger. So what the shit do you want from me, Jeff? Why is that not good enough to just stop right there? Where did this come from? It came from a sample. A sample could have natural variability. So the idea is I have to find a sample that beats the chance that it's just natural variability. It's got to be so far above the damn thing. For you guys, it would be this. It's got to be so far above where I would think it should be that it's evidence the mean isn't really here. It's probably higher, right? So not only does it have to be bigger, it's got to be far away enough. It's got to be way the hell out there. Okay. How do I put this into words then? If, in this case, T star is greater than 2403, we can say it looks like the guy who thinks it could be equal to it is wrong. If we're way up here, the guy who thought it should be here is wrong. And that's the null. I can reject the null. And if I can reject the one dude, that means I support the other dude. maybe. So there's only two things that can happen. Either I reject the null, which means I support the ha, or I fail to reject the null, which means I fail to support the ha. I can either say this one dude's wrong, which means it looks like the other dude's right, or I can say I can't show this one dude's wrong, which means I can't support the other dude's claim. Okay, maybe. Is that better, or am I just making it worse? You're like, I understand it less now, Jeff. Good job. Okay, all right, nobody's going to tell me. One little thing I wanted to see if you guys were cool with. The T star formula is the same as the Z star formula. It's the same formula. They basically mean the same thing. So I got a sample size of 51. X bar was what now? Yeah. Here's where people trip up. S was 1106.25. That's a sample standard deviation, but that's a standard deviation of individuals. Can't use that shit. I need the one that works for groups, because I got a freaking group, right? So I still have to divide it by the square root of n. It isn't, is it a population or a sample? It is it for individuals or is it for groups? That's what that is. Sigma and S are for individuals. I have to do this conversion to make it for groups. And what do you guys get for that? $150 something maybe? I don't know. 154.901?
Like 0 to 9 1. Oh my god, sorry.
All kinds of things. Sorry, 154.906? We have some dissension. Let's see. Bless you. Divided by square root of 51. 906. Yeah, okay. So this looks good. So then I calculate. So again, T and Z basically measure the same thing. But T's are built off of S and Z's are built off of sigma, right? So the formula is the same. It's still my data minus the supposed middle divided by the appropriate spread. Since this was built off of S, this is officially the formula for T. So what do you guys get? I think I know this. So I saw this on a few people's papers. I think this is right. 2.26? Is that what you guys got? Okay. Did we make it far enough away? No, we suck. We failed. We didn't make it far enough away. We don't suck. We're fine. We just didn't make it far enough away. So right here, I can write a quick little thing. We fail to reject the null. We fail to support the ha. Now, let me make a quick point. What was the very first thing we looked for to start this problem off? The very first thing we looked for. The claim. And then we forgot about it. We didn't give a shit about it no more until the end. So the claim gets us started. And then now I'm like, okay, now I got to word my conclusion based on the claim. Which one was the claim? The ha. Therefore, I want to use this language, not that language. So, we failed. We have not found, that's the word have, by the way. We have not found sufficient evidence to support the claim that what? You can say this a lot of different ways, but what was the claim? Yeah, college student credit card debt has increased. You could write it as, we have not found sufficient evidence to support the claim that college student credit card debt is now higher than 2806. I mean, there's a few different ways you could word that, right? Okay. So real quick, there's one thing I forgot on this side. And I will be very specific on a test or something. Can somebody look up the p-value for this? Negative 2.42. Let's see if you guys understand. I'm going to have to make one adjustment. So what's in the area of negative 2.42 z-score? The tail that makes. Sounds about right. Anybody else looking that up? You get 0.0078.
Yeah.
Now, real quick. Oh, you guys are gonna love this. How many tail tests was this one? This one. Two tail test, right? So the p-value is going to be twice this. So it'd be 0.01. You could do it, Jeff. I don't know. 5.6, I think. If you double 0.0078. Does that make any sense? Because what did we do to alpha? We cut it in half. We split it in half. So the full alpha is twice whatever it is in either tail. So p-value for a two-tail test, I just double the area that I get in one tail. Now, real quick. By the way, let me see if you guys are understanding this. How detailed is the z-score chart compared to the freaking t-score chart? What do I have here? No, that's no good. Do I have a z-score chart? You do, Jeff. There you go, buddy. Z-score chart, real quick. It's stupid detailed, yes? Z-score chart, lots of detail. T-score chart. If you think about each degree of freedom, it gives me very little detail, right? I want this to make all the sense in the world. I am never going to ask you guys to find a p-value for a t-test because you cannot get that specific with this. I would need this much information's worth for each degree of freedom. And if I were you, I'd say, that's fine, Jeff. So, y'all with me. If I used the calculator to conduct a test, it can calculate the p-value for t-score because there's formulas for that shit. Of course there are, right? So let me do one last thing. What time is it? Oh yeah, you guys, come on. You guys all look like you want things to end. Too bad. I'm going to show you one time because I'm never really going to do this. I want to conduct the test we just did, and I'm going to do it in the calculator just to show you. You don't have to know how to do this. I'm never going to ask you to do this. And if you use it to check your work, the answers are going to be a little off because the calculator doesn't round, but we do. Correct? Okay. So let me show you. Now I'm thinking to myself, do I remember how to do this? So you all agree with me that what we did was we just conducted a hypothesis test? So it makes sense to go to tests. This one specifically, what kind of test was it? Do you guys see all the options? This is some weird shit down here. Look, you can make intervals. Oh, Jeff is not telling you everything. Oh well. Z test, T test. So we're going to do a T test. Is that cool? in our future, there's going to be 2 sample tests, and that's more true to life. How do I test the efficacy of a drug? Don't I normally have at least a group that gets the real drug and a group that gets a placebo? Wouldn't they both be samples? Wouldn't that be 2 samples? All right, so that's in our future. Right now, we just have 1 sample. Let's see what this thing wants from me. So I can either tell it I put the data into a list, or I could just tell it I'm going to give you the stats, right? So what was the mean here? 2806. X bar was, where'd it go? 3156.2, yeah, 34. S was 1106.25. N was 51. And the test is greater than, right? You guys all with me? I don't know if you get the option for a color. I don't want to draw it anyway, I just want to calculate it. Let's see what it gives me. Does anything look familiar? What was our T-score? T-star? 226, right? 226. Yes? They calculated a p-value. Good for them. We can't, because we have this teacher that's stuck in the past using paper. What's wrong with this teacher? I don't know. And then it gives me useless shit. It was like, thanks, calculator, I already knew that shit. So the point of this is, if I did this in a calculator, I would just compare this to alpha. What was alpha? 0.01. So see how this is not less than that? So this would tell me that I fail to reject. I failed the test. And that's exactly what we did here. We failed, right? All right. So again, please, dear God, you do not have to remember how to do what I just did. I just wanted to show you, because it is something your calculator can do. So if you want to check your work, you can, but just be careful. It's not going to be exactly the same, because we round and they don't. Okay. All right, one last thing to talk about. I can't remember if I already said that, but if I did, I lied. Never listen to me. Okay. Except for when I'm lecturing. So I think I'm deciding between 2 things. And I think the most important thing is the type of error. In the homework, I don't know if anybody's gotten far enough where they talk about a type 1 and a type 2 error. The one beautiful thing about statistics is that there's always inherently a chance that we're wrong, even if we do everything perfectly. You don't get that shit in algebra, right? If you do everything perfectly, you're right. X is 7. Yay. Statistics says that because there's always most everything we're doing is based off a sample, and the sample we're not sure about. So the main thing that can come out of a test like this is I can either reject the null or I can fail to reject the null. Correct? That's the 2 things that can come out of a hypothesis test. Because if I do this, I automatically support the hop. So why write it down? And if I do that, I automatically fail to support the hop. So these are the 2 things that can happen. If I reject the null, when would I be wrong? So I think the null is wrong. I think the null is false. When would that statement be incorrect? When would I be wrong in my thinking? If the null was actually correct. So if I reject a true null, that is a type 1 error. that does not mean we did anything wrong in our analysis. So for example, going back for some reason to those spiders. If I take a sample of them and I do a hypothesis test about the average weight, and I get some answer, and I reject that their average weight is whatever, 11 ounces or whatever. Could their actual average weight be 11 ounces? Hell yeah, of course it could. I don't know. I just have a sample. I don't know. But I do the hypothesis test. I do everything perfectly right. And I still, and I say, I reject that their average weight is 11 ounces. And in reality, nature's kind of like looking down at me going, it is 11, man, what's that? So I would have made a type 1 error. Doesn't mean, again, it doesn't mean I did anything wrong in my mathematics. It's just frickin' real life. I'm gonna be wrong sometimes. Are you guys semi-cool with that? I'm gonna give you a non-mathematical example in a minute. So what's the thing? When would I be wrong to not reject the null? Fail to reject. Yeah, if the null is what? Incorrect or false. So if I fail to reject a false null, that is called a type 2 error. Jeff, I love this. Part of it's Roman, part of it isn't. I think officially it's Roman. I can't remember this book. No, I think this book does 1 and 2. So here is a non-mathematical example that we can explore. Let's say that we are a medic on a battlefield, right? And so it's our job to go out, and if I see anybody on the ground, I go up to them, and what is it that I'm doing when I come up to somebody who's laying on the ground? What's probably the first thing I'm going to try to check for? So I'm trying to check to see if they are alive. I love it. So there could be a little debate on what the null should be, but I would argue the null should be they're dead. Because what am I trying to find evidence for? I'm trying to find evidence that they're alive. I'm going to check the pulse. I'm going to check the breathing, correct? Right? Hopefully I'm not going to use my thumb to check the pulse. It's bad. Are you guys all with me? So what would the alternate be? Incredibly enough, the alternate would be the person is alive. You could argue there's a third one, that they're undead, but we're not going to entertain that possibility. Okay. What would a type 1 error mean? So you can now think of this in a real concrete example, right? What would a type 1 error mean? Well, I always like to start with this. In a type 1 error, what is reality? What is reality in a type 1 error? What is actually true in a type 1 error? The null. So in reality, they are dead. But I think they are alive. Good. Do you see how this works? So type 1 error, the null is true, so you can start there. In reality, they are dead. But I think, this is way too many words for me, they are alive. What would be the ramifications of that? What would I start to do then? First thing I do is, are they alive? If I think they're alive, what am I going to do now? Try to get their wounds dressed, see what's going on, try to diagnose them, try to do something, right? Are you guys all with me? So then I'm wasting time. Now, this is assuming that they are dead enough that I can't resuscitate them, right? So if I think they're alive and they're really dead, I am wasting time. So that's bad. Does everybody agree with me? Because then there's somebody else over there going, come on, man, right? And I know this is a little morbid, but most stats is. So it's just what would a type 2 error mean? What's the reality? In reality, the person is what? Is alive. But I think they are what? Dead. So, whoa, Jeff, that's a weird word. So I come up on them. I failed to reject a false null. So the null is false. So they are alive, and I think they are dead. I failed to reject a false null. So in this case, and again, this is a little bit of gallows humor, but somebody's on the ground. Guy comes over, like, oh, thank God, thank God. And then they run in like, no, where do you go? So that also would be bad. Does everybody agree with me? Here's the one little thing I haven't said yet. The reason we can change alpha is because alpha is the probability of making this error. Alpha is the probability, or at least close enough to it, of making a type 1 error. So if a type 1 error is really bad compared to a type 2, I'm going to make alpha smaller. If the type 2 error is worse, I'm going to make alpha bigger. Do you guys kind of follow? That's why alpha could change, and that's why everybody's got their own alpha depending on what situation it is. I don't know if that makes any sense to you guys. I'm not sure why it's so cold in here. Okay. That is play. So we're going to have a shorter class because hypothesis tests drain us. Yes?
Did you say alpha was the probability of making a type 1 error, or just error to code?
Type 1 error. Type 2 error is something called beta. So it's not exactly 1 minus alpha. There is a relationship, but it's not perfect, and we just don't have enough time to get into it. But if you want to look up the power of a test, that's a whole other level to this. Yeah.